we got three curves here. Y equals 0, which is a horizontal line. Let me draw it in red. X equals 2. Oh, sorry, I meant to change this. Let's just make it a little different. X equals 3. So 1, 2, here's where x equals 3, and so that's a vertical line. And then y equals x squared, which makes a parabola. Starts on that horizontal line and then collides with this vertical line over here. So this is the region bound by those three curves. And we're supposed to revolve this region. Should go all the way down here if I drew it correctly. We're supposed to revolve it around the x-axis. So this is the x-axis. So you got to picture that two-dimensional region being spun around in a circular fashion to make it a three-dimensional figure. So it makes kind of like a cone, but cones usually have straight edges on the side. This is going to have a curved edge to it. What's another shape this might be? Kind of reminds me of a tornado, where this is like the big part of the funnel, and this is the part that touches down on the ground. Okay, and the cone is also sideways, the ice cream cone, but remember, it's curved edges here. Okay, so we're supposed to find the volume of that, so we can use calculus to help us do that. And what we do is we use right cylinders. So remember, this is getting rotated around the x-axis, so it's going to come through here. So if I draw a right cylinder that looks like this, it's like on its side from how we traditionally draw it. There's our right cylinder, right? But we're just going to draw them to be infinitely small. Like maybe this one has a height of 1, because remember, the height of the right cylinder is the line that's perpendicular to the base. So I'm just going to put some numbers. Let's say the radius is 1, the height is 2. So the volume would be pi r squared times h, right? But obviously, if we had a height of 2, that would take up the majority of this graph. So a height of 1 would be a better approximation, because then we could fit 3 of them in here. A height of 0.5 would be even better. But what we're actually going to do is we're going to take an infinite amount of right cylinders. The height is just going to be approaching an infinitely small length. Okay, so we want to construct a function that represents those all those different cylinders. And so what we need to help us do that is an integral. We want to start at 0 on the x-axis. We want to end at 3 on the x-axis. And then the cylinders we're creating have a volume of pi, and then the radius of this cylinder right here, it starts on the x-axis and it goes up to wherever we are in this curve, right? So this radius right here of the cylinder I just drew is going to be different than this tiny little cylinder we're going to have to draw. Okay, where the radius is the distance from that curve to the x-axis again. So we need to, for the radius, we need a function that will always spit out the y value, the distance from the x-axis to the curve. And so that's right here, right? You give me a number for x, wherever we are on the x-axis, and you plug it in, and that will spit out the radius. So the radius is x squared. So pi r squared. Don't forget to don't drop a square. Pi r squared, and then h is that thing that we said is infinitely small, because we're taking an infinite amount of right cylinders. So dx is what we'll put here, because we're integrating with respect to x. Sorry, okay, so now the rest of this is the easy part. Constructing that's definitely the hard part. So I'm going to square that. It's pi, that's now pi times x to the fourth. And actually, we could just factor out that pi, because that's a constant. Okay, so we factored out that pi. Now we need the antiderivative. So that's x to the fifth over 5. And we evaluate that from 0 to 3. And so that's just 3 to the 5th power. I don't know what that is. Somebody does. Oops. 2, 3, 4, 5. So it's 243 over 5. So 243 pi over 5 is our answer. That's the volume of that tornado, of that cone that we were talking about.